All right. Wait, that's the wrong button. That's the right button. Okay, let's get started. Real quick, did everybody get one of the handouts?
I got one.
Okay, good. I'm glad.
Just in case you were wondering.
I was. All right, everybody, welcome back. Hope everybody had a relaxing Thanksgiving break. I'm already looking ahead. I'm looking to next semester. I'll admit to being in timber headspace right now. I've been thinking about timber, and how we're going to do that class next semester. So, okay, just a quick overview of housekeeping items for this class. So let's just go through the grades, okay? Your grade in this class is a function of 6 components: your attendance, your homework, the analysis project, and the 3 exams. So let's go through those. Attendance is up to date. The analysis project is graded. Everybody got your grades back. Class as a whole did very well. Okay. For the homework, everything that's outstanding on the homework is graded. And for the 3 exams, exam 1, exam 2 are graded. Exam 3 hadn't happened yet because that's the final. So what do we have left in the class? Okay. So we've got homework 9, which is the matrix analysis assignment. That's due Friday. I'm not accepting any late submissions on that because on Friday I'm going to give you the solution. Okay. So homework 9 is due Friday. I'm giving you the solution on Friday. Okay. Everybody okay with that? All right. Bonus assignment. I'm going to give everybody some bonus credit on top of their homework average if they upload proof that they did their course evals. Okay. Again, you can say I'm the worst professor ever. Just please do them. And all I want to see is uploaded proof that you did the evals. I don't want to see what you said. And it's something that I definitely pay attention to, especially in a class like this where I literally teach it every year. It's really easy to just think, well, it's going well. I just do the same thing every year. If there's anything that you think ought to be improved the next time the class is taught, please tell me. I do really appreciate the feedback. So homework number 9 and the bonus assignment are the only homework assignments that are left. And then our final is on Tuesday of next week. Most of you have 2 finals with me because we've got the structures final at 10:15, and then we'll have that final from 10:15 to 12:15, half-hour break, and then you have a materials final with me, 12:45 to 2:45, all on the same day. So I get a nice big old stack of things to grade next week all at the same time. Okay, sound good? All right, any questions on that? Everybody gets code? All right, so we've got 1 week left, and what I want to do is talk about matrix analysis a little bit more, and namely I want to talk about trusses, okay? So I want to start with what we've talked about so far, which is what happened with bar elements, and I want to see what's different from bar elements to truss elements, okay? So up here on the board, I put this sort of flow chart for matrix analysis, and let's just sort of get back into the headspace with how we do matrix analysis. And my main purpose for this content of the course is I want you to have a general understanding of how software performs structural analysis. Mainly because if you all become practicing structural engineers, you're going to have to diagnose problems with your models on your own. You're not going to have a Dr. Mike telling you, what to fix. And so you need to be armed with a little bit of information necessary to diagnose certain issues. That's kind of what my main reason for this. So, we could teach a whole course on matrix analysis. I've taken multiple courses on this, in grad school and all this. That's not my goal. My goal is to just cover the fundamentals, okay? And bar analysis is about as fundamental as it gets. Now, how do we go about doing a bar analysis? Well, we have 4 steps. The first thing that we do is we assemble a K-matrix for the structure. And if you remember the way that works, we write a K-matrix for each element, and then we assemble it into the K-matrix for the whole system. And remember, assembly is just putting each term where it goes in the big old matrix. And then if you have overlapping terms, you just add them together, right? Okay. The second thing that you do is you assemble a force vector for the structure. That was really easy. You literally just look at the structure. For bar elements or for bar systems, you can just look at the structure and do it. Okay? I have it as its own separate step in here for a very specific reason. We maybe talk about that a little bit on Wednesday. But I'll give you a quick peek into that. This part becomes a little bit more in depth for beams and frames because you have loads on the joints and loads on the members. So it's not as simple as just looking at the structure. You have to actually figure it out. Okay? Part 3 is solving for the displacements. You knock out the rows and columns associated with the boundary conditions and then solve for your displacements accordingly, just matrix analysis or matrix algebra. Once you've got your displacements, you're just sort of back substituting. You're computing F equals K delta for the whole system to get the reactions, and then getting a little displacement vector and doing F equals K delta for each one of those to get the forces in each element. And essentially, I have that written up here on the board. Okay? Now, what I gave you just now was a flow chart for trusses. Okay? Now, if you look at the flow chart that I gave you for trusses and compare it to the flow chart for bars, it looks like there's a lot more going on here, but there really isn't, okay? And I kind of want to make that point with just what I have here on the board. So here's the 4 steps, and I want to make a couple points. So first off, this step is the same. Exact same. This step, the same. So what changes? Okay, well, here's what changes. Okay, for part 1, we've got a little bit of an additional step that we have to do first. Okay, so the first thing that we've got to do in step 1 is we have to do what's called a transformation. So we start out with this Ke prime, and we have to do this. And then assemble. That's really the only difference with part 1, is that we have this little intermediate step that we have to do. We have to take each stiffness matrix and we have to transform it. And before you get worried that transformation is some fancy, really difficult to understand process, really this is just trig. That's all it is. This is just recognizing that truss elements are at different angles. Okay? So that's what makes bar elements versus truss elements. That's what makes trusses a little bit more intricate, is that we have to deal with some trig. Okay? The only other thing that we have to do that's different is right here. Okay? Instead of F equals K delta, we have F equals K prime times T times delta. And that's it. Other than that, the process is 100% exactly the same. Okay? And so the point I really want to get across is that, like, the same logic, the same procedure applies to if you're dealing with bar elements or if you're dealing with trusses. It's just the problems get a little bit bigger. Okay? And you can really start to see that computers and the ability to automate the process really does sort of shine as the problem gets bigger. Okay, so let's see if I can spend the next, 30 minutes, 40 minutes explaining this. Now, we do still need to recognize that we're going to be using matrix algebra, so let's just sort of get back into that headspace. We have 2 different types of matrices that we primarily deal with. We have square matrices and we have vectors. And vectors are just matrices that are of a single column. We could have vectors that are of single rows, but in structural analysis, we really don't deal with them that much. We either deal with square matrices or vectors the vast majority of the time. Okay? For 2 matrices, or for a given set of matrices, we have various algebraic operations that we can perform. We can add or subtract 2 arrays. They just have to be the same dimension. We can perform scalar multiplication. So scalar multiplication would be taking this and multiplying it by 4, or taking this and multiplying it by EA over L, or taking this and multiplying it by 6. You're just multiplying each term in that matrix by that. Okay? Now, we can also multiply two matrices. Now, in general, matrix multiplication is not commutative. Okay? A times B does not necessarily equal B times A. There are two common exceptions to that. That is in the case if you're multiplying by the identity matrix. A times I does equal I times A, and it just equals A. Remember, the identity matrix is just the multiplicative version of 1. Okay? And the other case of commutativity is when the matrices are inverses of one another. So when A multiplied by A inverse is the same thing as A inverse multiplied by A. And we ultimately do need to know how to do this because we are solving for displacements by inverting our K matrix. Okay? Again, you don't need to do this by hand. Software will do it for you, but you do need to understand it. Okay? We can invert a matrix if it is invertible. And so one of the things to keep in mind is that K matrices are not invertible, but K sub R matrices are. Once you've applied the boundary conditions, then it becomes an invertible system. And you can transpose a matrix. We're going to talk about transposing today. We're still going to apply the same ground rules, so joints and nodes, members and elements. This is going to be a little bit more important today for a couple of reasons. We're going to start including X and Y when we do trusses. The other thing is that this sign convention is going to relate to a different way of thinking about assembly. And we'll get to that here in a little bit. Okay, so let's talk about truss elements. Let's talk about them, and let's talk about how we can take what we've done so far with bar elements and apply them to a truss. Let's see if we can figure that out. Okay? So let's go back to this. This was our first element that we formulated. This was a bar element. We're just taking a bar and yanking on it. Okay? And what we said we said, okay, this bar element has an E, it has an A, it has a length. So we know that displacement equals FL over EA. So therefore, F equals EA over L times delta. And so this term EA over L is essentially the axial stiffness. And all the stiffness matrix is just EA over L terms. This is EA over L, this is minus EA over L, minus EA over L, and EA over L. That's all that is. It's just written in that matrix form. Okay. Now, I think bar elements are really nice to explain this process. The problem is that bar elements aren't really useful. We don't really build very many structures where all the bars all go in one direction. We're building structures like this, where we have elements going this way, and up and down, and left and right. And so what we do need to do is to take these mechanics and expand them to more real-world problems. Okay? So I want to take this 1D bar element and turn it into a truss element. Now I'm saying it's two-dimensional because I'm only considering X and Y. I mean, I could expand this to X, Y, and Z, but I'm not worried about 3D, at least for the purposes of this class. And as we talked about a long time ago, we really try and avoid three-dimensional analyses unless we can't in most civil engineering contexts. Sometimes we have to, but more often than not, we try and avoid it. Okay, so if I have a 2D truss element, I propose that what I need to do is to take this element and, back here, we said that each joint had 1 degree of freedom. This can move left to right, this can move left to right. Before a 2D truss element, we're just going to say each element or each joint can move 2 different ways. This joint can move left to right, or it can move up or down. This joint can move left to right or up and down. We just add a 2nd degree of freedom at each node. Okay? So the stiffness matrix for this truss element is just going to be 4 by 4. Okay? So how do we figure that out? Well, even though the matrix is bigger, it's still a bar. Okay? I want to be clear. The difference between a bar element and a truss element is we're just saying that the bar can move up and down. That's it. The truss element can move up and down. Bars can only move left or right, but truss elements can move left or right or up or down. Like it can move up or down, left and right, but it's still the same bar. It still has the same mechanics. It still behaves the same way. So I propose that the stiffness matrix, it's going to be the same stiffness matrix. It's just we're only putting the stiffness terms where they matter, okay? And I propose that the stiffness terms only matter on the first row and the third row, the first column and the third column. Why column 1 and column 3? Because 1 and 3 are associated with my degrees of freedom along the axis. In other words, what I'm saying is that this bar will respond axially. It will stretch or squish if you apply load along the axis, but anywhere else it doesn't have any stiffness. I mean, this comports with how we've been doing truss analysis this whole time. We said that truss members can either experience tension or compression. They don't shear, they don't bend, they don't twist, it's just axial, tension or compression. So we put our stiffness terms here, zeros everywhere else. And I propose this is the stiffness matrix for a truss element. It's that simple. Now, one of the things you might be wondering about is why do I have this KE prime? I didn't have that before. There's a reason for it. We'll explain that here in a bit. But just for now, recognize this is going to be my stiffness matrix for this truss element. If you want I guess a simple explanation, this KE prime corresponds to the local stiffness matrix. And what we have to do is take this local stiffness matrix and turn it into a global stiffness matrix. So maybe what I'll do here on my little flow chart here is I'll say that this is local, this is global. Okay, what does local and global mean? Bear with me. We'll get to this here in a second. Okay. All right. Everybody with me so far? Okay, so I want to give you a different way of looking at K matrices, because if you understand that, I think you'll understand this local and global and how we'll deal with the trig a lot more eloquently. So, how did we come up with this? How did we come up with this? We had this. How did we come up with that? Like, how did we derive this? Well, we took our bar element and we stretched it and squished it, and all we did is record the forces necessary to produce those said deformations. Okay? So, once we did that, all we did is we took those terms, we put them in a matrix, and that was our stiffness matrix. Like, that's basically what we did. I mean, this EA over L, it just came from this. Okay, so I'm going to ask you like a really simple math question. If delta equals 1, what is F? It's EA over L, right? Everybody with me on that? Okay, so that should be pretty simple. So I want to give you a different way of thinking about what is this term right here? What does this term mean? Like, what does this term mean? Like when I see this as a -1, like, okay, well, what is that -1? What does it mean? Okay, well, I propose that we can define the terms in these stiffness matrices as forces. Specifically, that some arbitrary term in a stiffness matrix. Because remember, stiffness matrices are these really big old table of numbers. And so Kij is some random term that's in the ith row and the jth column. Okay? I propose that a different way of thinking about these terms is that they're forces. More specifically, that it's, if we're talking about this term, it's the force at I due to a unit displacement at j. In other words, if the delta at j equals 1, that's what the force at I is. That's basically it in a nutshell. Okay? The reason why I'm thinking about stiffness matrices this way is because I want to think about assembly. See, when you assemble matrices, all you're doing is adding up forces. You're just summing forces in the x direction or summing forces in the y direction. That's all assembly is. Okay? So, how do we handle that? And I guess, maybe more specifically, what's the deal with this T matrix that's showing up? Well, let's take a look at this. So if these K terms are just forces, then essentially we're just summing up forces. Okay? Here's the problem. Okay? So if the members aren't facing the same way, we're going to have a problem when we start adding up forces. Let me kind of show you what's going on. Let's take this truss. See, I was looking into the future when I had this truss here. Okay, so here's a truss, and I've got 3 members in it, just 3 elements. Okay? Now, when I write the stiffness matrix for this element, let's take this element right here. So we'll call this E1. Okay? So when I look at E1, here's E1, I have 4 degrees of freedom. I have 1, 2, 3, 4. And so when I write that stiffness matrix, I'm assuming it's based on my degrees of freedom being formulated this way. But here's the problem. Let's take a look at, I don't know, element 2. Okay? Element 2 is sort of facing like this, right? Well, its stiffness matrix is going along that member, right? In fact, if I were to break up all of the members in the truss, they would look like this. So like, if I'm looking at the stiffness terms in each of these 3 members, they're going to go along the length of the member. I mean, this is what we said when we wrote these K matrices, that we're describing axial behavior. Stiffness along the axis, no stiffness anywhere else. Okay? That's what we did. So when we calculate a K matrix, the K matrix that we have now, when we're calculating it, we're getting a K matrix like this, a K matrix like this, and a K matrix like this. Here's the problem. Okay? The problem is assembly. Okay? This is what we have based on the mechanics that we've derived so far. But we can't really assemble this. We can assemble this. In other words, I need to take these and I need to rotate them. I need to take these and rotate them and rotate them and rotate and rotate, so that now they're all facing the same way. So now when I assemble them, the forces all make sense. They all line up. Okay? I can't assemble this matrix to this matrix because the degrees of freedom don't line up. Okay? So what I need to do is, for example, for this angled element, I need to take this and I need to do that to it. And how do I do that? It's just trig. Okay? That's all it is. Okay? Everybody with me so far? So I'm going to introduce some notation. Anytime in my problem that I have a prime, that's going to be associated with a local coordinate system. Anytime that I leave the prime out, it's associated with the global coordinate system. So in other words, local coordinates are with respect to the element in question. Global coordinates are the same for the whole structure. This is what I can assemble. I cannot assemble this. So here's the thing. For a given element, we can express things with respect to local coordinates, and there's an advantage. Local coordinates, it's really easy to derive a stiffness matrix. But expressing it with respect to global coordinates makes it easy to assemble. We need a means of switching back and forth. We need a means of switching from local coordinates to global coordinates. And how do we do that? We transform them with a transformation matrix. Okay? So what I need to do is figure out this transformation matrix. I need to figure out how to go from local coordinates to global coordinates and vice versa. Okay? So the way I'll describe, so the way I define that is that I say that local response equals T times my global response. So that could be local forces equals T times my global forces. Local displacements equals T times my global displacements. That's how that works. And this is an element by element operation. Okay? So there's no T matrix for the whole system. There's just a T matrix for each element. Okay? How do I get these terms? It's just trig. Let me show you how this works. So let's look at delta 1. So here's my element. Here's delta 1. I want to, delta 1 prime. I want to turn that into a global delta 1, delta 2. How do I do that? It's just this, right? Delta 1 times the cosine plus delta 2 times the sine. How do I do that for delta 2? Same idea. The only thing with this one is that delta 1 is going to go left, so my delta 1 term is going to be negative. Does everybody see that? So there's my transformation for delta 1. There's my transformation for delta 2. And by the way, we're going to get the same thing for delta 3 and delta 4. It's going to be written the same way. So all I need to do is I need to take these terms, I need to put them in a matrix. There's my T matrix. It's just trig. That's it. Okay? That is my transformation matrix. So by the way, I'm lazy. I don't want to write cosine of theta and sine of theta over and over again, so I'm just going to write C's and S's. Okay? That's my transformation matrix. It's that simple. Okay? So we never have to derive that ever again. We can just look at it. Now, transformation matrices have a very, very, very peculiar property. Okay? And that property is called orthogonality. Okay? This only happens, well, I mean, there's probably other matrices that this happens for, but with transformation matrices, it's really, really peculiar that if you transpose a matrix, it's the same thing as its inverse. Okay, and that's a really peculiar thing that happens with T matrices, but I'll show you how it works. So let's take a T matrix. Let's do a really small one. So let's do C, S, negative S, C. Okay? All right? So if I wanted to transpose it, you keep the main diagonal the same, and then you just swap the terms here. So this becomes S, this becomes minus S. Okay? Now, watch what happens when we multiply these two together. So you remember how we multiply them? We take the left matrix, stick it here, the right matrix, stick it up top, put the product down here. So we'll have C minus S, S, C. Put this one right here. So C, S, negative S, C. So my answer will go right here. So how do we get each term? We just do that and that, that and that. So how do we get this term? We do this times this plus this times this. So what do we get? C squared plus S squared, right? What does that mean, by the way? That means cosine, that means what? That means cosine squared plus sine squared. Anybody remember what that equals? That equals 1, right? So if I were to write this out, that would be 1. What about right here? Negative SC plus SC. That's going to be 0. What about here? Negative SC plus SC. That's going to be 0. What about here? Sine squared plus cosine squared. It's an identity, right? That only happens for this context, for structural analysis. That really only happens with rotation matrices, okay, with transformation matrices. Don't think that'll work with K matrices. It won't. K matrices, you got to invert. So I'm just using it for T matrices. Okay. Now, I can easily talk back and forth with displacements. I can easily talk back and forth with forces. But the whole reason for doing this is because I wanted to be able to assemble. So I need to be able to communicate between local K matrices and global K matrices. I need to figure out how to get from here to here. Okay? So how do I do that? Okay? Well, first I need to compute. Here's something that's kind of interesting. Have you ever noticed how when you model a truss, in masthead, you never have to actually tell masthead how long the element is. Why don't you have to do that? Well, masthead can figure out this is an x and y coordinate of this joint, and this is an x and y coordinate of this joint. And it can say, all right, I can get a delta x, I can get a delta y, I can say the length is the change in x squared plus the change in y squared, take the square root. You never have to actually tell masthead how long an element is, because it can figure it out, right? Okay? The one thing to keep in mind, so here's something, if we're talking about writing a program, we do need to be consistent, okay? And so typically what most software programs will do is it's got to compute delta x and delta y. The way that it will do that is it will start from the higher number joint and then subtract the coordinates from the lower number joint. So the idea is you go from the lower number node to the higher number node. So that's how you do that computation. Now, so that's how we calculate the length. How do we calculate the sine and cosine? Well, the sine and cosine is just adjacent over hypotenuse, opposite over hypotenuse. We never actually need to even compute that angle, okay? So if you notice here on your flow chart, there's a lot of formulas here for, you know, cosines and sines and delta x's and whatnot. That's because, I mean, this should be pretty simple, but you do have to compute that for each element. So how do we transform? Okay, so let me walk you through this. So let's start off with what we know. We know that if we were dealing in local coordinates, we know that f prime equals k prime times delta prime. That's what we know from mechanics. That's what we figured out right off the bat. But we want to be able to assemble globally. So what I'm going to do is I'm going to replace these local vectors with global. Local with global. I'm going to replace those. Okay? Next, what I'm going to do is get rid of the parentheses. It doesn't really matter in matrix multiplication. You just know that you can't switch the order anyways. Then I'm going to multiply both sides by T transpose. Why am I multiplying by T transpose? Because it's the same thing as T inverse. Over here on the left, T transpose T is going to cancel, and I'm going to be left with F. Over here on the right, T transpose K prime T. So that's where I came up with that. So that's why we're doing that. That's the process of rotation. Okay? So how do you do a truss analysis? Pretty simple once you understand that. So here's your procedure. Okay? Part one, we assemble the K matrix for the structure. Okay? So what do? We compute a K prime for each element. We compute a transformation matrix for each element. So we get EA over L, fill this in, transformation matrix, fill this in. And how do we compute those intermediate terms? It's pretty basic, right? Delta x, delta y, the length, the Pythagorean theorem, sine and cosine accordingly. Just whenever you compute your delta x and delta y, just go from the lower number node to the higher number node. So x of h minus x of L, y sub h minus y sub L. Next, we take these and we transform them. Very easy operation in Excel. And by the way, this right here, this is your problem 2 on the homework. I gave you a truss out of the textbook. I gave you an E value and an A value, and I just want you to tell me what KE is for one of the members. That's it. That's all I want you to do. I don't want you to do the whole problem start to finish. I just want you to do that part of it. Honestly, it's the hardest part. Okay? Next, we need to assemble. Okay? And I'm going to walk you through a start to finish example on Wednesday because I know I've got a lot of procedure and formulas today. Today I just want you to let it soak in, and then on Wednesday we'll go through and do one start to finish. Okay? So the resulting matrix, so here's the thing about matrix analysis, is that if you start doing real practical problems, these problems get really big. And they're not ones you would want to do by hand. They would not be very fun. For example, some of your projects, the projects that you all did, you would have very easily had matrices that would have been 80 by 80 or 60 by 60. That's not something you want to solve by hand. That would be miserable. Okay? But for a computer, you hit a button and it just does it. That's sort of the beauty of doing it this way. The force vector, we can just write it down. Okay? We got to be a little bit more careful with the bookkeeping, but in terms of the process, it is 100% exactly the same. As for solving for the displacements, again, 100% exactly the same. We knock out the rows and columns associated with our boundary conditions to go from a K and an F to a K sub R and an F sub R, solve for the displacements, okay? And this is definitely a place where using a software package, software is really great at doing this, okay? Excel's great at it. MATLAB's great at it. I know I brought up MATLAB and everybody doesn't like me. Just saying, like, it's really easy to do this stuff in MATLAB. I'm just saying. All right, I'm done. I won't mention MATLAB anymore. I won't mention it anymore. I'm done. I'm done. I promise. Okay. Next thing we do is we compute the final results, and it's pretty much the same process. Okay. We write a big old delta vector for the whole system. We just put zeros wherever the supports are, and the displacements that we just computed wherever they go. F equals K delta will give us the reactions, and then write a little delta vector for each element. F equals K delta will give us the forces in each element. We got to do a transformation, though, to get from delta to delta prime. I'm throwing a lot of details at you today. I don't expect you to, like, just start going at it today, because on Wednesday we're going to go through a problem start to finish. I went ahead and posted that problem, by the way. It's on Blackboard if you want to look at it. But we're going to do it together on Wednesday to make sure that we all understand it. But that's basically it. And I mean, this is not hard for a computer program to do. The other thing I really want you to take stock of is that it is standardized. Once you define the problem, it's good to go. In fact, I'll show you something. I will show you this. I'm not going to bring up the program that shall not be named, but I am going to bring up how a software package would store a given program, or store a given model. And I'll show you that with the problem that we're going to do on Wednesday, because I do think that's noteworthy. So let's take a look at this example, okay? So let's take a look at this example. So this is a truss analysis that you all could do in Mastham, or to be honest, you could do by hand. I mean, there's nothing stopping you from doing this problem by hand. You could do it right now, okay? But I do want to think about how a software program would store this data, and I'll give you an example of how a software program would store it. We only need to store two things. We need to store the information about the joints, or the nodes, and the information about the members, or the elements. Let's talk about the nodes. So how would a software program store the nodes? Well, how many nodes are there? Three. Okay? So what do we need for each node? Well, we need the X and Y data, right? So maybe node 1 would be 0, 0. Maybe node 2 would be 144, 0. Why did I write 144? Because I put it in inches. And this one would be 0, 108, right? So these columns would be the coordinates, okay? Now, I'm curious if somebody can tell me what they think are in these columns. What do you think that means?
The reactions.
The reactions. Node 1 is restrained in the X and Y direction. So I'm using just a little code to say this is X and Y restrained, this is Y restrained. Node 3 is completely free. Okay? And then the last thing I would do is that, which would be the loads, right? Those would be the loads that were applied to the system. So think about this, about your Mastham models. This table would be a lot bigger, but that's all mass 10 would need, right? For each node, it would need the coordinates, it would need to know whether there's a boundary condition applied, and if there are any forces applied. That's all it needs, right? Okay? What about the elements? How many elements does this truss have? Here, I'm going to make this is going to be a little bit wider. How many elements does these truss have? 3? So, what do we need to know for element number 1? Well, element number 1 goes from 1 to 2. Element number 2 goes from 2 to 3. And from 1 to 3, right? So we need the nodes. The other thing that we need are the E values and the A values. Bless you. That's all we need, okay? That's all we need. Think about, like, the data file that MassTan stores. I mean, like, we can solve the entire problem with this. This is all the information we need. I mean, think about how big your Call of Duty save file is. And then, like, this is all we need to do a complete structural analysis. Like, it's really, really conservative in terms of data storage. It doesn't take a lot of room, you know. Now, again, your projects, more rows, more nodes, more elements. But that's it. This is all that MassTan is storing in order to do a problem start to finish. And then think about the procedure. Think about how it's going through and doing these step-by-steps, right? Like, think about this. So, like, think about, like, this step, this part 1. Like, how would a computer program do this? Well, it would say, okay, I need to compute a K matrix and a T matrix. So, for each one of these rows, it'll say, okay, let's look at element number 1, okay? So I need the X and Y coordinate for joint 1 and the X and Y coordinate for joint 2. Once I get that, calculate delta X, delta Y, calculate the length, calculate the sine, calculate the cosine, write this. Then just do it again. Then just do it again. You see what I mean? See how it's like, it's pretty procedural how you can write this out. It's not that difficult, you know. I mean, you can write a program to do this start to finish in a surprisingly few lines of code. I have a program that will do your homework 9, problem 1 in less than 20 lines of code. Like, it's not that much code. It's really quick. So it's surprising just how efficient you can be with this stuff. So,
Can you share that code with us?
no, I will not. It would involve you opening up the program that shall not be named.
I think they will bringing it up.
I didn't bring it up. He asked. I didn't say the word. All right. Any questions? I'm giving you 7 minutes of your life back, everybody. I'm going to pull up the code. That's all I got, everybody. I'll see you all on Wednesday. Actually, I'll see you tomorrow. For materials.
What about
Well, you should go.
instantly? No.